In this video, we continue our discussion of colligative properties, paying particular attention to boiling point elevation. Now, freezing point depression and boiling point elevation can be used to determine new freezing or boiling points. They can also be used to determine concentrations and molar masses. And so we'll look at examples of all of these. And so our first example here, we're asked for the boiling point of a 2.5 molal glucose solution. So we're looking for boiling point. And if we're looking for boiling point, we know that we have this equation that tells us that our change in our boiling temperature equals K times M times I. We are given the concentration. We've got that concentration of 2.5 molal. Now, we assume our solution is aqueous unless we're told otherwise. So that being the case, we're going to use the K value for water here. What we need to determine is going to be our I value, our Van Hoff factor. So we've got to determine if this substance is an electrolyte or a non-electrolyte. So we've got glucose. We've looked at glucose before. It's an organic compound, it's a molecule, it's a non-electrolyte. So if it's a non-electrolyte, that means its I value is 1. So plugging in the information that we have, we put in the K value for water, so that's that 0.512 degrees Celsius per molality. So we had that in a previous video, times our concentration, 2.5 molal, times our I value of 1. And that is going to give us a temperature change of 1.28 degrees Celsius. Now this tells us how the boiling point of our solution changed. It is the amount by which the boiling point increased. We're looking at boiling point elevation, so this is how our boiling point increased. Now our solvent's boiling point is 100 degrees Celsius. We're dealing with aqueous solutions that are the most common. You've got to know your boiling points and freezing points for water. So we've got to know water boils at 100 degrees Celsius. Now, my solvent boiling point plus that temperature change is going to be equal to my solution boiling point. So my solvent started at 100 degrees Celsius. We just determined it's going to increase by 1.28 degrees Celsius, which will give us a new boiling point of 101.28 degrees Celsius. Now we can also figure out freezing points. So we're going to look at the same concentration solution, a 2.5 molal glucose solution, and we want to know the freezing point. Now the only difference here compared to example 1 is that we're going to use Kf, which is the freezing point depression constant. And we're going to subtract that temperature change from the solvent's freezing point. So our equation looks the same. It's delta T equals K times M times I. So this time we're plugging in the K value, Kf value, the freezing point depression constant for water, which is 1.86. So again, this is a constant. It was given to us in a previous slide. The concentration, again, is this 2.5 molal concentration. And we've already said glucose is a non-electrolyte, so its I value is 1. So that's going to give us a temperature change of 4.86 degrees Celsius. Now this tells us how the freezing point of the solution changed. It's the amount by which the freezing point decreases, because again, the property is freezing point depression. So my solvent freezing point minus my temperature change will give me my solution freezing point. My solvent, again, is water. Its freezing point is 0 degrees Celsius. That, again, is something we've got to know. So 0 minus my temperature change of 4.86 is going to give me a new freezing point of negative 4.86 degrees Celsius. So we've just looked at 2 examples. We looked at it calculating a new freezing point and a new boiling point. In both of those examples, we used the K value for water, but we had a glucose solution. So we're being asked here in problem 4, why did we use the K values for water? And that is because K depends on the solvent only. Now in example 1, we used a boiling point of 100 degrees Celsius. That is because that is the boiling point of my solvent, my water. Now, if our glucose were dissolved in ethanol instead, which the problem would have told us we had glucose in ethanol, would we use the same values? And the answer is going to be no. Again, K depends on the solvent. We used the K values for water when water was the solvent. If we're using a different solvent, we're going to use different values. We would have to use the K values for ethanol. Now, in example 1, where we were looking at boiling point elevation, once we found our temperature change, we added our temperature change to the original solvent boiling point. So why did we do that? Well, again, remember that our property is boiling point elevation. So if we're talking about an elevation, that's the amount something increases. So if we're increasing something, we're adding to it. So that's why we added the change to our initial boiling point. Now with example 2, we looked at freezing point. And in that example, we subtracted our temperature change from the original solvent freezing point. And that's because the colligative property is freezing point depression. So depression means to decrease something. And so if we're decreasing, we are subtracting. Now, in those two examples, the concentration we were provided with was in a molality. Now, again, if we're in a laboratory and we're using pre-made solutions, they're generally not going to be labeled in molality. And we need to know what that concentration is in molality. And most commonly, we're going to see containers labeled with either molarities or percentages. And we've got to be able to take that concentration and convert it. So looking at example 3 here, we're asked for the boiling point of a 25% aqueous ethylene glycol solution. So again, we're looking for boiling point. If we're looking for boiling point, we've got that equation we can use, that the delta T equals K times M times I. So we know that our solution boiling point, since it's aqueous, is going to be the original boiling point plus the temperature change. So 100 degrees plus our temperature change. And we know that our temperature change equals K times M times I. We know that K is 0.512 degrees Celsius per molal because that is the K value for water, which is my solvent. And then we've got an I value of 1. That's because that ethylene glycol, C2H6O2, contains all nonmetals. And therefore it has covalent bonds, which makes it a non-electrolyte. So the only thing we're missing in order to determine that temperature change is we need a concentration in molality. What we have is our concentration in mass percent. So remember when we talked about mass percents, 25% means that we have 25 grams of our solute in 100 grams of solution. So we can take that and break it down. To get molality, we're going to need moles of our solute, and we're going to need kilograms of our solvent. From that mass percent, we know the mass of our solute. So we can say we've got 25 grams of solute because that's the amount contained in 100 grams of solution. So we're just taking our solute mass here and we're converting it to solute moles. Using the molar mass of that ethylene glycol, which is 62.08 grams per mole. So we set up our conversion so that the grams cancel. We're left with moles of ethylene glycol, and we get 0.403 moles. Now, the other thing we know is that if I've got 25% as my concentration, then 100 is my solution. And my solution is my solvent plus my solute. So if I subtract my solute amount from my total solution, that's going to give me my solvent. So 100 grams of solution, 25 of which are solute. We subtract the two, we get 75 grams of water. Now I have the information I need to get my molality. So I'm plugging in my moles divided by my moles of solute divided by my kilograms of solvent. So 75 grams is 0.075 kilograms. And we're getting a concentration of 5.37 molal. So now that we have our concentration in the appropriate units, we can find our temperature. So plugging in, delta T equals KB times M times I. So our K is the 0.512 degrees Celsius per molal, because again, that's the K for water. We have an aqueous solution. We're going to plug in the molality we just determined, the 5.37. So this is what we just found, and this should be a lowercase m. And we're going to find that our temperature change is 2.75 degrees Celsius. Now, the question we're asked is the boiling point. So the boiling point is of my solution. It's my original boiling point of my solvent plus my temperature change. So our new boiling point is going to be 102.75 degrees Celsius. So in this example, we used ethylene glycol. We're asked, why did we use that I value of 1 in that example? And again, that's because we are dealing with a non-electrolyte. So how would this problem be solved differently if we happen to have had an electrolyte solution instead? We'd still go through the same mathematics steps. We'd still have to get our percentage turned into molality. But the difference is going to be the I value. I would be something other than 1. And since that'll be the case, we would multiply by some different value. So it might be an I value of 2 or 3, depending on that particular ionic compound or that particular electrolyte. So here we've looked at an example or examples of how we can calculate a new boiling point or a new freezing point for a solution based on the concentration of that solution. We've looked at an example of using molalities directly or taking a concentration and having to convert it to molality. In our next problem, we'll take a look at some additional practice with taking a percentage and converting it, and we'll look at an electrolyte rather than a non-electrolyte.